energy theory. So I'll give the definition, and then we'll go ahead and calculate what it means to fail under this theory. And of course, we'll draw a plot which looks a plot on sigma A, sigma B axis. Yes, so this theory states that yielding occurs when the distortion energy distortion strain energy per unit volume reaches or exceeds the distortion energy per unit volume in a simple tension or compression experiment. Okay, and all you do in the same material, that's when you do the test in the simple tension compression, you do it to the same material, the same material. Okay, so I'm going to just break this down. Okay, so we need to compute the distortion energy per unit volume first. What does it really mean to compute the distortion energy, strain energy? That's the first step. The second thing is once we compute that, we better find what is the distortion energy per unit volume in a simple tension or compression experiment. So that's the second thing we'll do. So we'll have two values. One is the value from distortion strain energy for a general loading. We'll also get the distortion energy per unit volume in a simple tension compression experiment. And all we do in the end is we set this condition, reaches or exceeds greater than equal to. Okay, so how do we go about computing distortion energy? This is how you do it. Okay, consider a cube. And let's say that, well, it's subjected to some general loading, but we have managed to compute the maximum principal stresses, which is easy to do now that you know how to compute the Morse circle. So once we have this, we can break it into two parts. One is a stress, let's call that sigma average, and I'll give you what that value is. Okay, sigma average, and the sum of these two should be equal to the sum on the value on the left, which means that the stress here would be sigma 1 minus sigma average. So if you sum this with this, you get sigma 1. Same for this one, sigma 2 minus sigma average, sigma 3 minus sigma average. So this is the general stress. It's broken into two parts, a hydrostatic part and a distortion part. Okay, what is this sigma average? It's basically the average stress, sigma 1 plus sigma 2 plus sigma 3. Okay, so this uniform stress, which acts on all the walls of this cube, it's hydrostatic. It is so to say it's uniform, it's going to lead to uniform stress in all directions. So when you subtract the average part from individual stresses, you lead to the part which actually leads to distortion of the cube. So I guess the way it's defined makes sense. This is B, this is C. So what we'll do is, in order to compute, we need the energy here. We need the energy in this case. Energy C is unknown. This is the one which is determining the failure theory. So what we'll do is we will use, well, we know that energy is the same if you, no matter how you compute it. So energy in A should be energy in B plus energy in C. When I say energy, it's basically the energy due to the stress. So in order to compute the energy in C, which is the unknown, you simply take energy in A minus energy in B. So this is this minus this. So now it's just a matter of figuring out energy in A and energy in C. Sorry, energy in B, so we can get energy in C. Okay, so let's do that. Let's compute energy in A. Energy in A, that would be simply, so the energy for anything which is loaded is simply half stress times strain. So all you do is take the strain in the direction of 1, strain direction of 2, and strain direction of 3. You can compare, you can check this with the units. The strain times the stress gives you the energy. Now you can also sub in the value for strain. We know that the value for strain is nothing but 1 divided by E, sigma 1 minus Poisson's ratio, sigma 2 plus sigma 3, and so on. Right? We've seen this relation before. So we can write the strain energy in direction 1, strain energy direction 2, and so on. So if you do this math, you get energy in A as, so since we substitute strain as a function of stress, the energy in A will only be a function of stress. And that comes out to be this value. Sigma 1 square, sigma 2 square plus sigma 3 square minus 2 nu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Okay, so this is our expression 1. We'll need it later. Okay, the second part, the energy due to the hydrostatic part. So we need to compute this. Well, it turns out that we simply substitute sigma average equals sigma 1 equals, sorry, sigma average is sigma 1 plus sigma 2 plus sigma 3 divided by 3 in expression 1. That's all we need to do. We already computed a simplified formula for the energy as a function of stress. So we just use that. We put sigma average to be sigma 1 to be sigma 2 equals sigma 3 equals sigma average. Sorry, this should be in 1. And then we'll have an expression for energy in B. Simply 3 times 1 minus 2 times Poisson's ratio divided by E, sigma 1 plus sigma 2 plus sigma 3 divided by 3 square. So this is 2. Okay, now we are all set to compute the energy due to a distortion. It's simply 1 minus 2. Okay, let's do that. Part C, energy in C is 1 minus 2. So I will not write that down, but I'll just give you the final expression. So if you write that energy, the distortion energy as dE, then the distortion energy is given by 1 plus Poisson's ratio divided by 3 times E, sigma 1 minus sigma 2 square, sigma 2 minus sigma 3 square, sigma 3 minus sigma 1 square divided by 2. This is our final expression. We'll need this. Okay, so what we have achieved here is we have computed a formula for the distortion energy per unit volume. That's all we have done. Now, let's do this part. Let's compute the distortion energy per unit volume in simple tension compression experiment. So to do that, so simple tension compression. All we are doing is we are taking this material, clamping it down, and then just stretching with some stress. So we need to compute the distortion energy due to uniaxial loading. So how do we do that? Well, it's simply sigma 1 will be Sy. This is sigma 1. Sigma 2 and sigma 3 are 0 because it's the uniaxial loading condition. And all we do in this case is substitute the value of sigma 1, sigma 2, and sigma 3 in expression 3. So substitute in 3, we can compute dE as 1 plus nu divided by 3E Sy minus 0 square plus 0 square plus 0 minus Sy square divided by 2. Okay, so it comes out to be dE equals 1 plus nu divided by 3E times Sy square. Yes, so this is 4. Okay, so we've now computed the strain energy due to uniaxial loading. That was the second part. We've computed this, we've computed this. Now we only need to set the condition that when the distortion energy in your given loading reaches or exceeds the distortion energy to simple tension, that's when the material will fail. Okay, so that's all we do. Okay, so let's set that. So we just set dE failure occurs when three, which was computed here, exceeds 4. So all we do is we write down 3 and we write down 4 and then put the greater than equal to sign. So sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Okay, I can do some save myself some time by just realizing that I can chuck these off. They basically will cancel off. So I'm only left with this part in the bracket. With this divided by 2 is greater than equal to Sy square. I'm going to do a step where instead of trying to keep it this way in terms of squares, I just think I'm better off just taking the square root here. So this will drop off. And then I'll have to put this all under a square root sign. And actually, I would like to define a new quantity called sigma prime. So let's call this whole thing, just move it. Okay, let's call this quantity here as sigma prime. Okay, this is just to denote the stress due to distortion. It also has a name, actually. It's called the von Mises stress, after a person who probably discovered it. So von Mises stress is given by this expression. When this stress exceeds the stress Sy, that's when you'll have failure due to distortion energy. Okay, so that's the final expression. So all you do is you compute von Mises stress and you set it equal to Sy. Okay, now we can do this step which we've done earlier, which is for a two-dimensional case, can we compute the von Mises stress and compute the failure criterion? That's what we'll do next. Okay, so let's do that. Okay, so let's compute distortion energy for 2D case. Okay, we know very well that you would have two stresses, sigma A, sigma B, and it's not really important if they are greater than 0 and so on. It won't really matter here. And then the third one is always 0. Okay, so we substitute. We can just put that in the von Mises stress, sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square divided by 2, and then we need to take the square root. Okay, so we sub this value here, sigma A minus sigma B square plus sigma 2 is sigma B minus 0 square plus sigma 3 is 0 minus sigma 1 is sigma A divided by 2 and square root sign. Okay, so when you simplify this, you get sigma A square plus sigma B square minus sigma A sigma B raised to half, which is the square root, is greater than Sy. So this is the equation which determines the failure for a 2D case. Failure criteria for distortion energy theory. Okay, so this, just like we had figured out the conditions for um, maximum shear stress theory, we can actually do the same thing with this equation, which means that we can now plot this equation on the sigma A, sigma B axis and see how it looks. Okay, so I'm going to make a plot of this particular equation on the sigma A, sigma B axis. Okay, if you recognize, this looks sort of like a circle, but it's not a circle, actually the equation of an ellipse. This is the equation of an ellipse. So let me draw that. Okay, so this boundary is the MSS boundary. This boundary is the DE boundary. So if you have the yellow region, this is the failure, no failure using the MSS criterion. And then for the other one, which is yellow plus the blue, that is the both regions, you need to consider both those regions, you will have no failure due to DE. So this equation, the D equation, remember, is what I wrote down here. It's this equation, it's the equation of an ellipse. So that equation is showing up here. It's sigma A square plus sigma B square minus sigma A sigma B equals SY square. That's the equation of the outer ellipse. Okay, so as I said, this region is safe for MSS as well as DE. Okay, but the blue region, all the blue region, not just this, but entire blue region, is safe for DE, unsafe for MSS. That is, in this region, the blue region, the theory says that the material will fail if you use maximum shear stress criterion. It will not fail if you apply the DE theory. Okay, because the yellow region is, the area in the yellow region is less compared to the area in the DE theory. That is, the yellow region is within the, or the MSS is within the D. It is we can conclude that MSS is more conservative than D. It's a very small region, right, as you can see, but it is more conservative. That is, MSS will let you choose a smaller stress, right? Anything here is smaller than anything in the blue region. And so when you apply the stress, the MSS theory, to design something, you will end up with bigger diameter, because bigger diameter means smaller stress. And because it's a larger or bigger diameter, it's called a conservative theory, because it will not really give you it'll make things more safer, or the factor of safety will be higher if you use MSS. Okay, so that's like the most important thing. Now let's get to design using MSS, D. Just like we looked at design using MSS, okay? So first thing is the factor of safety, or design factor. That's simply SY divided by the von Mises stress. I wrote down the von Mises stress earlier. This is one formula which you'll use. The other thing we have to know is sometimes we want to, so von Mises, the way I've set sigma is that it basically uses the principal stresses, but you can actually compute von Mises based on sigma x, sigma y, and tau xy. How do you do this? Well, we look at the transformation which relates principal stresses to sigma x, sigma y, tau xy. So because sigma prime is, what did we write? Sigma 1 minus sigma 2 square, sigma 2 minus sigma 3 square, plus sigma 3 minus sigma 1 square. We can also relate sigma 1, sigma 2 with tau xy. This is an expression I wrote down a long time back when we talked about Morse circle. Okay, so what you can do is you can sub in the value of sigma 1, sigma 2 here, and of course sigma 3 is 0, and then get an expression for sigma prime. Simply, so let's do this systematically. So let's call this 1, let's call this 2, I'll call both these equations 2. So all we do is substitute 2 in 1, and we have sigma prime is sigma x square sigma y square minus sigma x sigma y plus 3 tau xy square, the whole thing raised to half. Okay, so this is your von Mises stress in terms of sigma x, sigma y, tau xy. So you don't really have to go through the process of computing the principal stresses. You can just use this. Okay, now what we have talked so far with DE is only looking at experiments involving tensile tests. What if you use DE for shear experiments? So we could also use DE for shear. Okay, so we can maybe do it here. So we're going to use using the distortion energy theory for shear experiments. That is, the main mode of failure here is shear, or there's no principal stress, sigma x, sigma y, but there's shear stress. So if you put sigma x equals sigma y equals 0 in this expression above here, then you have let's call this 3, then we have sigma prime is going to be 3 times tau xy square raised to half. So it's square root 3 tau xy. And so this can be written down as what's square root of 3? I think it's 0.577 maybe. 1.732. Okay, so it's, I have to after all move this to a new page. Okay, so this gives me the sigma prime as 1.732 tau xy. Okay, I also need to compute the same thing for for the uniaxial test. So put sigma x equals sy and sigma y equals tau xy equals 0. So this is in 3. So if I put sigma y 0, I get sigma sy sy. Let me check something. Yeah, that's right. So that's what you get. And now we can, all you need to do is equate this quantity to this. So we have 1.732 tau xy equals sigma sy. And so we can compute tau xy. So it's 1 divided by 1.732. It's 0.577 3 sy. So this is how you would use distortion energy in a pure shear experiment, because the failure in shear experiment is tau xy. Okay, so another way of interpreting this is if SSY is yield strength in shear, then SSY is 0.5773 SY, and so then tau XY equals SSY. It's just another way of interpreting the same thing. If you defined a new yield strength in terms of shear, that would be 0.5773 SY, and then you can just say tau XY is shear strength SY.